Hello everyone, today we are going to study the analytical method used in stability analysis of a gravity dam, and it is included in the module 4 of design of hydraulic structures of civil engineering semester 6 of APJ Abdul Kalam Technological University. Now in the analytical method we use this method to calculate this or to analyze the stability of a gravity dam, and the stability of the dam can be analyzed in the following steps. That is, step 1, we are considering unit length of the dam here, that is 1 meter length. That is, if we have a cross section like this is a height and this is a width, and we are considering unit length. That means this is 1 meter. Okay, so we are considering unit length of the dam, and the dam extends to both the sides. So we will be considering 1 meter length of the dam for calculation in analytical method. Then step 2 is to work out the magnitude and directions of all the vertical forces acting on dam and their algebraic sum, that is sigma v. We need to calculate all the vertical forces acting on the dam and calculate its sum. And step 3 is to calculate all the horizontal forces and their algebraic sum, that is sigma h. Then after that we have to determine the lever arm of all the forces about toe. That is, toe means for the cross section this is toe and this is heel. So we need to find out the lever arm, that is, if this is a self weight of the dam W, lever arm is this distance. We need, for all the forces, we need to calculate the lever arm. Then step 5, we need to determine the moment of all forces about the toe and find out the algebraic sum of these moments. That is, if we are considering self weight, the moment is W multiplied by this distance, let it be x. So moment is W into x, and it goes in anti-clockwise direction. Okay. Next, we need to find out the location of the resultant force by determining the distance from the toe. To find out that, we have x bar is equal to sigma m by sigma v. Here let us consider the cross section of the gravity dam like this, and we have, this is a sigma v acting along this line, that is sum of all vertical forces, and this is all sum of all horizontal forces, and the resultant of these two will be going through along this line, and this x bar is the distance from the toe to the point of intersection of this resultant with the base of the dam. So we need to find out this x bar, and for that we have x bar is equal to sigma m by sigma v, and after that we have to find out the eccentricity of the resultant using E is equal to b by 2 minus x bar. That is, eccentricity is the distance between resultant or the point of intersection of resultant with the base of the dam and the midpoint of the base. That is, if this is b by 2 and this is also b by 2. Okay, we have eccentricity is equal to E, that is equal to b by 2 minus x bar, that is this distance. Okay, this distance. Okay, now it must be less than b by 6 in order to ensure that no tension is developed anywhere in the dam. Now step 8, we have to determine the vertical stress at toe and heel using the equation of vertical stress, that is Pn is equal to V by B into 1 plus or minus 6 E by B. Okay. Step 9 is to determine the maximum normal stress, that is the principal stress acting at toe and heel, and they should not exceed the maximum allowable values, that is the maximum permissible stress of concrete or whatever material that we are using for the gravity dam construction. So we have sigma 1, that is a Pn sec square phi minus P tan square phi, where Pn is the normal stress, phi is the angle made by the sloping face with the vertical. So this is the angle phi. Okay, phi. And P or P dash is the tail water pressure. Okay, this is P dash. And so sigma 1 is equal to Pn sec square phi minus P dash tan square phi, where P dash is a pressure due to tail water. Also find out the shear stress during the using the equation, which should not exceed the permissible stress, that is permissible shear stress. The tau is equal to Pn minus P dash into tan phi. So here we are moving on to the numerical problem, and here the figure shows the section of a gravity dam which is built on concrete as a non-overflowing section. That is, there is no spillway available or constructed on this cross section. And neglecting the earthquake effects, we have to calculate the maximum vertical force at heel and toe. Okay, this is a heel and this is a toe of the dam, and major principal stress at toe of the dam, and intensity of shear stress on a horizontal plane near the toe. And weight of concrete is given as 23.5 ton per meter cube, and we have to assume the unit length of dam for calculations. And also, permissible stress in concrete is given as 2500 kilonewton per square meter. So this is a figure. We have 6 meter is the top width, and top level is 289 meters. Water level is at 285 meters, and this point where the downstream slope starts is at 280 meters. And this is the alpha or phi, as we earlier studied from that equation. This is the angle, that is the angle between downstream face and vertical of the dam. And slope of downstream face is given as 2 horizontal is to 3 vertical, and tail water level is at 211 meters, and base of the dam is at 205 meters. And there is a gallery given, it is drainage gallery given at 8 meters from the heel, and total width of the dam is 56 meters. Okay, now we need to calculate, first we need to calculate all the loads coming on this dam cross section. And for that we have, first, this red color triangle is a hydrostatic pressure diagram, and this is a force due to water P1 acting at h/3 from the base. Okay, and here h is 80, and this small triangle is a hydrostatic pressure diagram due to tail water, and that force is P2, and it is also acting at small h/3 from the base, and whereas here small h is 211 minus 205, that is 6 meters. Also, we have drainage gallery at 8 meters from the heel, and remaining distance is 48 meters. Then we have the uplift pressure diagram. This is the uplift pressure diagram, and we have usually the uplift pressure diagram is a simple triangle then when there is no tail water. Okay, and when there is tail water, it will be shaped as a trapezoid. Okay, and when a gallery is associated with it, at the gallery there will be a sudden change in the shape like this. Okay, this is the usual shape of uplift pressure diagram when a drainage gallery is provided. Okay, so in this problem, first we need to calculate, as we have said earlier, all the loads. First we have to calculate P1, then P2, then we have divided this uplift pressure diagram into 4 parts. That is this triangle, and the load due to this triangle is U2, and this rectangle, and the force due to this rectangle is U1, then this rectangle, and the force due to that rectangle is U3. Then we have this triangle, that is this triangle, and the force due to that triangle is U4. And what we do is that we simply find out the area. Okay, for example, to find out P1 is given by area of this triangle, that is half into, this is gamma h multiplied by h, that is equal to half gamma h square. Okay, similarly P2 is equal to, this is gamma into small h, so half gamma small h square, that is P2. Then other forces are, we have to find out the self weight of the dam, and that is, take this as W1, that is this rectangular portion. We are dividing this cross section of the dam into 2 parts, that is this rectangle and this triangle, and we will be calculating the self weights separately. So W1 and W2, that is simply take the area of this portion, that is 6 meter, it is W1 is equal to 6 meter into then 8 meter multiplied by 1, that is unit length of the dam, multiplied by the weight of concrete given, that is 23 ton per meter cube. Okay, so it is 23 kilonewton per meter cube. So that's how we calculate. Similarly, we will be calculating W2, that is by taking the average of this triangle and then multiplying it with the unit weight of concrete. Then remaining is the force due to uplift. And for that, first we need to find out this ordinate, okay, this ordinate or this length. Okay, to find out this height, okay, this height is required so that we need to find out all the area of this different components, that is this rectangle, then this triangle, then this rectangle, and this triangle. So we need this height for area calculation, and that height is given by gamma into small h minus h by 3. Okay, and here gamma is a unit weight of water, then small h is a tail water height, capital H is a upstream water height, that is equal to 80. So by doing this, or by solving this equation, substituting the value of gamma h and small h and capital H, you will be getting the height of this portion. And if you get this, you can find out this height by subtracting that value from gamma h, and you can find out the area of all these portions using the dimensions provided. So let us see. Okay, this table shows the calculation for all the forces that is coming on this cross section of the dam, and let us see, this is the type of force, that it is self weight, weight of water, water pressure, uplift, etc. Then designation, that is just what we are going to name that particular force, that is W1, W2, etc. Then we have magnitude in kilonewton, then whether the force is horizontal or vertical, and both are in kilonewton. And if the horizontal force, if it is towards the upstream side, that is in this direction, then it is taken as positive, that is a sign convention. And if it is in the downstream direction, then it is negative. And for vertical forces, downward forces is taken as positive, that is downward forces are taken as positive and upward forces are taken as negative. Then we have lever arm, that is about toe, that is from toe, that is there from this point. All these forces we need to find out the lever arm. For example, if you are taking this force, this is the lever arm. We need to calculate the lever arm for all the forces. Then we have moment about toe, that is in kilonewton meter, and clockwise moments are taken as negative and anti-clockwise moments are taken as positive. Now let us go to the calculation, and for first component is a self weight W1, and W1 is the weight of the dam due to this rectangular portion, that is this portion, okay, this rectangular portion. And for that we have unit weight of concrete given as 23.5 kilonewton per meter cube. Okay, now for that we to calculate the forces, we need to find out the volume of this rectangular portion, that is height of that rectangular portion is 84, that is 289 minus 205, that is 84 multiplied by width, that is given as 6 meters, 6 multiplied by unit length of the dam, as we have said earlier. We are considering unit length of dam for calculation. Then that multiplied by this unit weight 23.5 will give you the force due to, that is the weight of the dam due to that rectangular portion, that is 11,844, and it is taken, it is in the downward direction, so as per the sign convention it is positive. So that is what we have calculated here. This is a force W1 and it is in downward direction, so it is taken as positive. Next we are going to calculate the self weight of the dam second force, that is W2, and W2 is due to this triangle. This is W2 and this is a self weight due to this triangle. Okay, so that triangle is having a height of 280 minus 205, that is equal to 75 meters. So height of that triangle is this much, that is 75 meters. Now base width of that triangle, that is 56 minus 6. Don't confuse it with this 8 and this. 8 meters is actually the distance of this gallery from the heel of the dam. So here the triangle that we are considering is having a height of 75 meters and base width of 56 minus 6, that is equal to 50 meters. Therefore the area of the triangle is half multiplied by 75, that is height, multiplied by 50, that's a base width. Now into 1, that is a unit width length of the dam that we are considering, multiplied by the unit weight of concrete given in the question as 23.5. So that is what calculated here. This 0.5, that is half multiplied by 50 into 75 into 1 into 23.5, and that is obtained as 44,063, and that is also in the downward direction, so it is taken as positive. Now let us calculate the lever arm. So for W1, that is W1 comes here. Okay, this is W1 and it acts through the centroid of this rectangular portion. So the W1 will be base. Okay, let us draw it again here. Okay, this is a rectangular portion, so it acts through this line, that is W1, and that is a midpoint of this 6 meter width. Okay, so 6 meter, so this is 3 meter, so this is the top of the dam. So lever arm is this distance, therefore that is 3 plus base width of this triangle, that is this much from here to here, that is, we have already found it out as 50, that is 3 plus 50. So lever arm of W1 is obtained as 53. So moment due to W1 is this force multiplied by this lever arm, and that you will be getting as 6,27,732, and that force will be acting in this direction about, that is the moment will be acting anti-clockwise, and the anti-clockwise moments are taken as positive. And similarly for force W2, okay, for W2 let us see, let us draw it again here. W2 will be, this is a triangular portion. Okay, so W2 will be acting along the centroid of this triangle, so this is W2. So distance of this W2 from, or the line of action of W2 from toe will be this much, and that is equal to, for a triangle the centroid will be 2 by 3 into base width. Okay, this is 2 by 3 into B, that is B is this distance, that is we have already calculated it as 50. Therefore that lever arm is equal to 33.33, that is obtained by 2 by 3 into B, where B is 50. So 2 by 3 into 50, that is equal to 33.33. That is the lever arm of this second component of self weight. And again moment is equal to, this is the load, so this is the direction which the moment acts. So that moment is anti-clockwise, and its value is 14,68,620, and it is anti-clockwise, so we are taking it as positive. So now we have completed W1 and W2. Now we are moving on to W3, which is the weight of water on the downstream face, and that is the weight of water due to this small component. Okay, so to calculate that, we need to find out the area of this component, and the triangle looks like this, and it is having a height equal to the tail water height, that is 211 minus 205, that is equal to 6, and this distance is equal to 4. Okay, that is calculated using this slope given. Now area of the triangle is equal to half multiplied by 4 into 6 into unit length, that is 1, multiplied by unit weight of water, that is 9.81. So this is half into 4 into 6, that is a base width and height of the triangle, into length of the, that is unit length that we are considering, multiplied by unit weight of water, that will give you the force as 118 kilonewton, and that also acts in the downward direction through the centroid of this triangle. So it will be along this line, and the centroid of that triangle will be at a distance of, this distance is equal to 1 by 3 into 4, that is 1/3 of this base width. So that is equal to 1.33, that is a lever arm. Now moment about tau is equal to this force multiplied by this lever arm, that is equal to 157, and that is also acting in the anti-clockwise direction about 2. Therefore it is taken as positive. Okay, now next we are going to calculate the water pressure, that is P1 and P2. That is P1 is due to the upstream water and P2 is due to the downstream, that is tail water. So to calculate P1, the force P1, that is due to the hydrostatic water pressure on the upstream side. Okay, for that this P1 is equal to area of this hydrostatic pressure diagram, and the base of the hydrostatic pressure diagram is equal to gamma h, where h is the height of water. H is the height of water, that is equal to 80. So area of that hydrostatic pressure diagram, that is a triangle, is equal to half into base is gamma h, that is 9.81 into height, that is 80. So gamma h equal to 9.81 into 80. So that is a base width multiplied by height, this height. Okay, that is equal to 80. So that is P1 is equal to 9.81 into 80 square by 2. That is gamma h square by 2 is the force due to that hydrostatic pressure diagram. So that sums up to 31,392, and according to our sign convention it is acting in the downstream direction and it is horizontal. So it is taken as negative and it is written at the portion corresponding to horizontal forces. Now next we need to find out the lever arm. Lever arm is this height from toe. Okay, this is a toe and this is a level of toe and this is a lever arm height. So that is equal to h by 3, that is equal to 80 by 3, that is obtained as 26.67 meters. So to find out the moment, we multiplied this 31,392 by 26.67. You will be getting the value of moment as 8,37,225, and it is acting in, see, let us see, this is a force and this is a point, so it is acting like this. Okay, so the moment is clockwise and clockwise moments are taken as negative, so it is written as negative here. And then we have the tailwater pressure, so this small triangle. So we need to find out the area of the small triangle, that is height is 6 meters and base width is 6 into 9.81. So area is half into 6 into 6 into 9.81, that is this is a height and this is a base width. Okay, that is written here, 9.81 into 6 into 6 by 2, that you will be getting it as 177, and it is acting in the upstream direction. So upstream forces or upstream direction is taken as positive, so 177 and it is written as positive. And lever arm is for this triangle, lever arm or this force will be acting at h by 3, okay, at this level. So that is equal to h by 3, which is equal to 6 by 3. So that is 2. So moment is obtained as this 177 multiplied by 2, that is equal to 354, and this force will be imparting a moment in this direction, that is an anti-clockwise direction. So anti-clockwise moments here we are taking it as positive, so write the value as 354 and it is positive. Okay, next we are going to calculate the forces due to uplift pressure. So this is an uplift force diagram, and here we have divided this diagram into 4 parts, and there is 4 forces, that is U1, U2, U3 and U4. Okay, and in the previous slides I have explained how to calculate this ordinate. Also, after dividing this diagram into 4 parts, that is U1, U1 is this rectangle, that is the force corresponding to this rectangle, then U2 is the force corresponding to this triangle, and U3 is the force corresponding to this rectangle, and U4 is the force corresponding to this triangle. So we have to find all of this separately and then finally find out the lever arm and moment. Now to find out U1, that is this pressure value or this force value, we need to find out first, we need to find out this height or this ordinate, and that is given by gamma into small h minus, sorry, small h plus capital H minus small h by 3. Okay, so that is equal to 9.81 multiplied by small h, that is a tailwater height, that is 6, that is this height. Okay, plus capital H is this upstream water level 80 minus small h, that is 6 by 3, that is equal to 300.86 kilonewton per meter square. Okay, so now we have to find out the force due to this, or force due to this rectangle, that is U1. So that is given by that height that we found out just now, this height, that is equal to 300.8. 300.8 multiplied by width of that triangle, that is the width of that rectangle, that is 8, that is U1 is equal to 300.8 multiplied by, that is height of the rectangle multiplied by width of the rectangle, that is 8 multiplied by unit length, that is 1. Okay, that is equal to 2406, and here the force is upward force, so according to the sign convention we are taking it as negative. Okay, now lever arm of that particular force will be 48 plus, that is 48 is this length. Okay, this length, this is 48, so that is from here to here it is 48. 48 plus half of this value, that is 8, so that is 48 plus 4, that is equal to 52. So lever arm is 52. Therefore moment about toe, moment of this force about this toe is equal to 52 multiplied by 2406, that is equal to 1,25,112, and that is in the, about the toe it is in the clockwise direction, and clockwise moments are taken as negative, so it is, we are noting it as negative. So we have found out U1. Next we have to find out U2. U2, that is this force. Okay, this force U2, and for that we have that, if we draw that uplift pressure diagram again, we have to find out the force due to this triangle, that is U2, and we have found out this value as 300.8, and this total height, this is gamma h, that's equal to 9.81 multiplied by 80, that's equal to 784.8. Therefore this remaining height is 784.8 minus 300.8, that's equal to, this is equal to 484. Therefore for this triangle we need to find out the force due to this portion of the uplift pressure diagram. Therefore we have to find out the area of that triangle, that is half into height of the triangle is 484 multiplied by width of that triangle is 8 multiplied by unit width, so that is equal to, so here it is given for finding out U2, it is half, that is 0.5 into 484 is the height of that triangle, this one height of the triangle, multiplied by width, this is a width, or here this is a width, that is equal to 8, and height is, this height is, this is 484, and this is 784.8, and this is 300.8. Therefore 784.8 minus 300.8 is 484. For 0.5 into 484 multiplied by 8 is the width of that triangle, and by multiplied by unit length, so you will get the value as 1936, and it is also in the upward direction, so it is upward negative, so 1936, and it is negative. Now we have to find out the lever arm. Lever arm is a distance from this point to center of this triangle, that is this distance. Okay, this distance, so that is equal to, lever arm is equal to 48, that is up to this point it is 48. This is 48 plus centroid of this triangle, that is centroid of this triangle will be at, if we draw that triangle again, centroid of that triangle will be at this gap length is 8. So centroid will be at along this line. So this is 2 into 8 by 3. Therefore lever arm is equal to 48 plus 2 into 8 by 3, where that is 2 by 3 of 8. That is, for this triangle, the centroid will be at a distance of this distance 48 plus 2 into 8 by 3. So 2 into 8 by that is equal to 52.33. Now multiply this force into this lever arm to get the moment of U2 about tau. That is equal to 103, that is 1,03,247, and that is also in the clockwise direction. So that is also taken as negative. Okay, now we have found out U2. Next we have U3 and U4. To find out U3, there is a force due to this small triangle. Okay, we have, if we enlarge that, this is U3. Okay, and height is gamma into small h, that is equal to 9.81 multiplied by 6, that is equal to 58.9. And this length, that is this length is 48. This is 58.9. Therefore we have area of that rectangle is 58.9 is the height multiplied by length 48 into unit length of the dam, that is 1. So multiplying that, you will get the value of U3. Its magnitude of U3 as 2837, which is also acting in the upward direction. So it is taken as negative. And lever arm is the distance from this point to the center of that, or centroid of that rectangle, that is 48 by 2. This is 24. So lever arm is 24, that is this distance is 24. Now moment is 2837 multiplied by 24, that is 67848. So that is also in the clockwise direction. Therefore it is taken as negative. Now next is the moment due to, or force due to this triangle. Okay, that's a triangle below that. If you draw it here, this height is, this entire height is, we have found it, or we have found out it earlier, this is 300.8. So this is total height is 300.8, and this is 58.9. Therefore this height is 300.8 minus 58.9, that is equal to 241.9. Now you have to find out the area of this triangle. Okay, that is half into, that is U4 is equal to half into 241.9 multiplied by base width, that is 48 into unit length, that is equal to 1. So you'll be getting the value as 5806, and this is also in the acting in the upward direction. So that is equal to, that is taken as negative. And lever arm is, the base width of the triangle is, this is 48. So the centroid will be acting along this line. So this is 2 by 3 into 48. So that's equal to, lever arm is 2 by 3 into 48, that is equal to 32. And hence multiply force with lever arm to obtain the moment, that is 185792, and it is also in the anti-clockwise direction. So that is also taken as negative. Now we have found out all the forces W1, W2, W3, P1, P2, U1, U2, U3 and U4. Now we need to find out the sum of all horizontal forces. So it is 31392, that is negative, plus 177, that is positive. So you will be getting sigma HS 31215, and it is in the, it is towards the downstream, that is towards right. Now next, sigma V. After summing up all this, you will be getting sigma V as 43050, and it is positive, that is in the downward direction. Okay. Next is sigma M. Sigma M is 777639, and that is also obtained as positive. Okay, so that is positive, and it is in the anti-clockwise direction. So now we have found out all the values. Now moving on. Now we have already calculated all the forces coming on the gravity dam based on the cross section that is given. Now we have to do the stability analysis and to check if the dam is safe in different criteria like overturning, sliding, tension and compression. So for that, first we are going to consider, as always, we are considering unit length of the dam, and distance of the resultant from the toe is obtained as, that is distance of the resultant from the toe. We have discussed this in the during discussing the steps. For that, if this is a sum of horizontal forces and this is sum of vertical forces, and if this is a resultant, this is x bar, this distance from the toe, and that is obtained as sigma m by sigma v. That is sigma m we have found out earlier in the previous table, that is 777,639 divided by sigma v, also we obtained from that table. So you will be getting x bar, or the distance of the resultant from the toe of the dam, is obtained as 18.06. Now we need to find the eccentricity. So eccentricity is the distance between midpoint of the base and the resultant. So that is b by 2 minus x bar, that is 56 is the width of, or base width of the dam. 56 by 2 minus x bar, you will be getting eccentricity as 9.94. Now we need to calculate the vertical stress. So for vertical stress, we have discussed the equation earlier. PV is equal to sigma v by b into 1 plus or minus 6e by b. So sigma v as obtained previously, that is 43050 divided by base width is 56 into 1 plus or minus 6 into eccentricity is 9.94, we just calculated, divided by 56. So you will be getting it as 768.8 into 1 plus or minus 1.065. Now this positive, that is 1 plus case, is for the maximum vertical stress, that is a P max will be at the toe of the dam, that is maximum vertical stress will be at the toe of the dam, and for that we are taking this 1 plus 1.065 condition. So 768.8 into 1 plus 1.065. So you will get the value of maximum vertical stress at toe as 1587.6. Okay. Now minimum vertical stress will be at heel, that is P minimum at heel is obtained by this 1 minus 1.065 condition, and you will be getting the values minus 49.97 kilonewton per meter square. Now after this we need to find out the major principal stress at toe, and for that we have the equation sigma is equal to PV, that is a direct stress at toe, multiplied by sec square alpha minus P dash, that is a tail water pressure, P dash multiplied by tan square alpha. Okay, now for that we have PV toe, we just found it in the previous slide, that is 1587.6 kilonewton per meter square, and P dash is the tail water pressure, that is a pressure due to this hydrostatic pressure diagram, that is gamma into small h, that is 9.81 into 6, we'll be getting it as 58.9 kilonewton per meter square. Now after that we need to find out tan alpha. Okay, we are given the slope of the downstream faces, 2 horizontal is to 3 vertical. So this is alpha. Therefore, that is not alpha. This is alpha. So tan alpha is equal to 2 by 3. So alpha is equal to 33.69. Tan alpha equal to 2 by 3 and alpha equal to 33.69. Now substituting the value of alpha, P dash and PV toe in the equation of major principal stress, you will get the value of major principal stress as 2267 kilonewton per meter square. And as the above value is less than 2500 kilonewton per meter square, that is a permissible stress of concrete as per the question. It is given in the questions. As this value is less than the principal stress, this value is greater than the principal stress, the structure is safe, and we can say that the structure is safe in compression or crushing. So safe in compression or crushing. Okay. Next we need to find out the intensity of shear stress on a horizontal plane near the toe, and for equation for shear stress near toe is PV toe minus P dash into tan alpha. So substituting the values, we get the value of shear stress as 1019.1 kilonewton per meter square. Now next we need to check the stability against overturning, sliding, compression and tension. So compression and tension, compression we have just already done. So first check for stability against overturning, and we know that check stability against overturning. The factor of safety against overturning is given by sigma mr by sigma mo, that is righting moment by overturning moment. That should be greater than 1.5. So first sigma mo is the sum of all clockwise moments. That is from the previous table we have to find out the sum of all clockwise moments, that is negative moments. So you will getting the values 13,19,224 kilonewton meter. Now after that you have to find out the sum of all anti-clockwise moments, that is a MR, that is a resisting moments. So that is a moment due to self weight and tail water pressure. So you will be getting the values to 20,96,863. Now factor of safety is equal to MR by MO. This is MR, this is MO, and you will be obtaining a value of 1.589. So the obtained value is greater than 1.5, hence the structure is safe in overturning. Next we are going to check the safety against sliding, and for that we have factor of safety is equal to mu into sigma v by sigma h, and it should be greater than 1. Here the value of mu is not given, that is a coefficient of static friction, it is taken as 0.75. So substitute the value of sigma v, sigma h, etc. as we obtained from the table, and mu you will be getting the factor of safety just above 1, that is 1.0022. So you can take it as to be safe in sliding. Now after that, safety against crushing or compression, that is the maximum stress developed is equal to the principal stress, that is sigma 1, and we have found out sigma 1 as 22,267 kilonewton per meter square, and permissible stress is given as 2,500 kilonewton per meter square. So this permissible stress is greater than sigma, hence it is safe in compression or crushing, and that we have just did in 2 or 3 slides ago. Now next is safety against tension. For safety against tension, the eccentricity should be less than b by 6 and Pn at heel should be greater than 0. This is a condition. For that, here we have b is equal to 56 and E eccentricity was obtained as 9.94. Now b by 6 is equal to 9.33, and here E is greater than b by 6. So we can say that the structure is not safe in tension. And we have obtained the value of this Pn heel, that is a principal stress condition. When we found out the principal stress, b by 6 into 1 minus 6c by b condition, 1 minus condition, you got the value as negative 50 something. Okay, so that is you got the value less than 0. It should be greater than 0. So less than 0 means tensile forces. So tensile forces arise. So as the structure is a concrete structure, the development of tensile stresses are not desirable because this concrete structure is very weak in tension. So we need to avoid that condition. But although here the value is very small, that is only approximately 50 kilonewton per meter square is arising, that is minus 50 kilonewton per meter square, that is 50 kilonewton per meter square tensile stresses are arising at the toe at extreme pressure conditions, that is a maximum. Even there is maximum water plus maximum uplift condition, in such extreme conditions only this tensile or this small tensile force value is arising. So it is considered to be okay, although it is unsafe, it is sometimes considered to be okay for very large dams with very large heights. So now we have completed all the required stability criteria. We have calculated all the loads based on that different stress diagrams. Then we have calculated all the forces coming on this cross section by using the table. We have tabulated everything in the table. Then we found out the direct stress, then principal stress, shear stress, eccentricity, etc., etc., and also we have found out the factor of safety in compression, then overturning, not factor of safety in overturning, then sliding, then safety in compression and tension. So that's it. We have completed the whole problem. So thank you.